Hello and welcome to this video lesson on enthalpy changes, spec reference 3.1.8.1, and here are our learning objectives. So firstly, let's have a look at this one. This is the one that where we need to understand that enthalpy change is the heat transferred in a reaction at constant pressure, and of course you'll be familiar that the symbol is delta H for enthalpy change. Okay, so that's the first thing we want to do. Second thing, let's have a look at this one. We need to remember from before that exothermic reactions have a negative delta H and endothermic have a positive delta H. And we'll make sure we remember that. Thirdly, we need to understand what lattice enthalpy is. And there are actually two ways that it can be defined, and we need to know both of those. And lastly, in this video lesson, we're going to learn these 8 definitions. We have 8 definitions to learn: enthalpy change of formation, bond association enthalpy, enthalpy change of atomization for elements and for compounds, ionization energy, electron affinity, enthalpy change of hydration, and enthalpy change of solution. 8 definitions that is imperative that you remember word for word, and so we'll go over those, and in class we will practice them. So let's move on. Okay, let's just remember some of the basics. So for an exothermic reaction, our enthalpy change is negative, and so let's write it like this for now. Whereas for an endothermic reaction, our enthalpy change is going to be positive. So we'll write it like that. And the thing to remember is about a negative enthalpy change is that the amount of energy left in the chemicals has decreased, and that is the energy that has been released to the atmosphere, and so as heat. And the corollary is true with an endothermic reaction, which is a positive enthalpy change. The bonds in the products have taken in energy. They contain more energy now, and they've had to get that energy from the surroundings. And so that's how the heat energy is taken in from the surroundings. Okay, so that's the negative and positive bit. Let's just recap on this little symbol here that you might see sometimes. This refers to standard conditions, and the standard conditions, as far as temperature are concerned, would be 298 Kelvin and 100 kilopascals pressure. They're the two standard conditions. And lastly, you might remember that the enthalpy change could be for a reaction, in which case you might see a little R. It could be for combustion, in which case you might see little c, or also there is formation, in which case you'd see a little f there after the delta H, formation being formation of a compound from its elements. So now we're going to consider what is lattice enthalpy, and I can tell you that lattice enthalpy is the energy that's in the bonds of an ionic lattice, and so it's a measure of the strength of the ionic bonding. And we can define it in two ways. The first way is the lattice formation enthalpy, and this is when we start off with gaseous ions, 1 mole of each, and we turn that into the ionic lattice. So the lattice formation enthalpy for sodium chloride, as we got here, is when we make 1 mole of the ionic compound from its ions that are in the gaseous state. So notice the state symbols there on the ions. And in this case, the lattice formation energy is minus 787, and the units are kilojoules per mole, minus 787, so that indicates that this process is exothermic. Energy being given out to the atmosphere. Okay, so that's the first way of defining lattice enthalpy. The second way of defining lattice enthalpy is the lattice dissociation enthalpy, and that's when we start with the lattice, we start with 1 mole of the ionic compound, and we make gaseous ions out of that, and so we break down that lattice, break all those bonds, and the lattice dissociation enthalpy for this compound would be 787 kilojoules per mole. And notice that that is a positive 787, and so we can say that the dissociation enthalpy here is endothermic, in that we've had to put energy in to break those bonds in the ionic lattice. Now in the last slide we noticed that the lattice enthalpy of formation of sodium chloride was minus 787 kilojoules per mole. But how do we actually determine that minus 787? And determine is just another word for working out. Well, the unfortunate thing is we can't do it directly, and so we have to do it in various parts. And these are the parts. First being that you need to make gaseous atoms from the elements. So in our example, we started off with sodium, and normally that would be in the solid form, and so we would have to get sodium atoms in the gaseous form. And our chlorine normally would be existing as Cl2, and so you would have to get chlorine atoms in the gaseous state from the chlorine molecules, also in the gaseous state. So this step here would be known as the enthalpy change of atomization, and you'll need to memorize a strict definition of enthalpy change of atomization. So that's the first step. The second step is that atoms of one element, in this case sodium, lose electrons to form positive ions. So our element is sodium, and now we've got sodium, a gaseous sodium atom, and we're going to make a gaseous sodium ion out of that. And that step is called the ionization energy. And in this case, it's the first ionization energy because we're taking off the first electron from the gaseous atom. But if we were starting with that sodium ion and turning it into a sodium 2+ ion, then of course that would be the second ionization energy. And that's another strict definition you'll need to memorize. But moving on to the third step. Third step is for in our case, for the chlorine, where we take the atoms and we let them gain their electrons to form the negative ions. So we've got our chlorine gaseous atom, and it's gaining an electron, and it's going to make a chloride ion. Let's gaseous, and let's just be complete and put our electron back up there for the sodium ion. And that third step, where the chloride ion was made, is called the electron affinity. Affinity as in attraction. Okay, fourth and final step is actually our lattice enthalpy, and so we've now got a positive ion and a negative ion. Our positive ion, of course, is our sodium ion, and our negative ion is our chloride ion, both gaseous, of course. And we let them form their solid ionic lattice, and in this case give out their energy. And that step, as we now know, is our lattice formation enthalpy. So we're going to make out of these two, when we add them together, we're going to make our sodium chloride. And that sodium chloride would be solid at standard conditions. Now, when we want to determine the lattice enthalpy, it's the last step that we're interested in, and so we might need what's called a Born-Haber cycle in order to calculate that from a bunch of experiments that work out the total energy change and some of the individual energy changes, and from all of those different calculations you can find the lattice formation enthalpy. That's the topic for the following lesson. So that's this lesson nearly complete, and we just, as usual, check off all of our learner objectives. The first one, that the enthalpy changes the heat energy transferred in a reaction, which can be combustion, formation, or a normal reaction. At constant pressure, you remember that was 100 kilopascals, and while we're at it, 298 Kelvin. And we also came across or reminded ourselves of the delta H sign for our enthalpy change, and we also added the standard state symbol in as well. Okay, so we reminded ourselves that exothermic reactions have negative delta H values, where heat is given out to the atmosphere because there's less energy in the product bonds, and in an endothermic reaction, heat is taken in to make new bonds that have more energy, and so that is a positive delta H. And we looked at the two ways of defining lattice enthalpy, that being formation and dissociation. And then there's a bunch of definitions which we looked at quickly, but I'm going to leave it for you to fine-tune those definitions and memorize them word for word. And that's 8 definitions. Please do that before the class lesson. Thank you. Hopefully that's been clear, and I'll see you in class.